Hey students, welcome to the last lecture of Linear Algebra 2. So this will not be really a lecture, but in this video we want to review a little bit and also do these review exercises for your preparation for the final exam. So if you're not interested in all of these exercises, you can find timestamps in the description below. So here we see that the topics we covered during the course. So recall that we started with the notion of vector spaces. So these were some sets together with two operations, addition and scalar multiplications, and these satisfied certain rules. And then we talked about linear maps between vector spaces. So these were maps which behaved well with respect to this vector space structure, which meant that, for example, that f of u plus v equals f of u plus f of v. And here this plus was so if f was a map from v to w, then this plus here was the addition in w, and this plus here was the addition in v. And also if we had a scalar, then the scalar could go outside of this f. And then after this we talked about matrices for linear maps. So for this we needed to choose a basis, and then we saw that for finitely generated vector spaces these linear maps corresponds to matrices, or we can assign to a linear map a matrix after choosing a basis. And then we talked about determinants. So determinant were a number which you could assign to a linear map or to a matrix. And one important property was that if the determinant of a linear map or a matrix is non-zero, then this linear map or this matrix is invertible. And after this we talked about eigenvalues and eigenvectors. So if we had a linear map f, then v was called an eigenvector if f of v is just lambda times this v, and if this v is non-zero. And to calculate these eigenvalues and eigenvectors, we considered the determinant of the matrix A minus lambda times the identity matrix. So more precisely, we considered the characteristic polynomial of a matrix or of a linear map. And then the zeros of this polynomials were these eigenvalues. And to get these eigenvectors, we needed to solve some linear equation and calculate the kernel of a certain map. And then in the end, we talked about linear differential equations. And for all of these topics, we will do now some examples or exercises. And we will start with the exercise number 1. So in this exercise, we consider this following matrix, this 3×3 matrix. And the first exercise is to compute the determinant of this matrix. And so in this case, how we calculate the determinant? So in general, we had a formula for the determinant of a 3×3 matrix. But in this case, it's easy to see that the determinant of this here is just 1 times the determinant of this matrix here. So in this case, the determinant of A is just the determinant, or 1 times the determinant of this matrix. So this is what we call the Laplace expansion. So here, if we have a column or a row with a lot of zeros, then we expand with respect to this column. And here in this case, we just get the determinant 4. And second exercise is find all eigenvalues of A, and then for each eigenvalue, calculate the eigenspace. So to calculate the eigenvalues, we need to consider the characteristic polynomial of this matrix, which we denoted by PA lambda. So this is a polynomial in lambda, and this was defined by the determinant of A minus lambda times the identity matrix. In this case, is 3×3 identity matrix. So this just means we take the determinant of this matrix A, where on the diagonal we subtract lambda, 2 minus lambda. And this, again with the same argument as before, this is just 1 minus lambda times the determinant of this matrix, 2 minus lambda. So this is 1 minus lambda times 2 minus lambda squared. So the zeros of this polynomial here are clearly lambda equals 1 or lambda equals 2. So the eigenvalues are lambda 1 equals 1, lambda 2 equals 2. And then the eigenspaces, so let's do the eigenspace for lambda 1. So in this case it's the eigenspace for 1 of this matrix A. So these are all the space of all eigenvectors for this eigenvalue plus the 0 vector, and this we define to be the kernel of A minus 1 times identity matrix, or in general, if I have lambda here, it's the kernel of this. So in this case, it's just the kernel of the matrix A, where I subtract 1s on the diagonal. So this is just 0, 5, 4, 0, 1, 0, 0, 0, 3, 1. And this is the same as the kernel. Here, with this I can remove this one, and with this I can remove this. So the row-reduced echelon form of this matrix looks like this. And therefore the kernel is given by the span of 1, 0, 0. So this eigenspace here is spanned by this vector 1, 0, 0, and the eigenspace for the eigenvalue 2. In a similar way, this is the kernel of the matrix A, where we subtract 2s on the diagonal. So there it's minus 1. So here we need to plug in 2. So it's minus 1, 5, 4, 0. And here now it's 0, 0, 0, 3, 0. And this is again the same. We learned that if we consider the kernel of a matrix, it's the same as the kernel of the row-reduced echelon form of this matrix. So we need to consider the row-reduced echelon form here and see that this has a shape 1, 1, 0, 0, 0, 0, minus 4. So here, because I can divide by 3, then this is a 1, then I can remove this 5 times from there, so I get a 0 there, and have a 1 there. So and then I can change these rows, and this, then I can multiply by minus 1. And therefore we see that this is now spanned by 4, 0, 1. So this is here a vector, an eigenvector for eigenvalue 1, and this is a vector for eigenvalue 2, and these two span the eigenspaces. Okay, and we also see that in this case here we just get one solution, but here the algebraic multiplicity of this eigenvalue is 2, so it could have been the case that we actually get a two-dimensional kernel here, but we see that in this case we just get a one-dimensional kernel. Okay. And now the third question is A diagonalizable and or invertible and or orthogonal? So first question, is A diagonalizable? So diagonalizable would mean that we can find a basis made out of eigenvectors. So here in this case our space is three-dimensional, we are in R3, and we just find these two eigenvectors. So we will not find a basis, and more generally we prove the following fact. So let me bring this up here. So we had this corollary that a map F, or a matrix A, is diagonalizable if and only if the sum of the dimensions of the eigenspaces equal the dimension of the whole space. So in this case here, both eigenspaces have dimension 1, and the dimension of the whole space is 3, and therefore this is not satisfied here. So A is not diagonalizable. diagonalizable. Because the dimension of E1a plus the dimension E2a, so these are both 1. Oops, 1 plus 1 is 2, and this is not 3, which is the dimension of the whole space. And, well, if then the second question is A invertible, well, the determinant of A is 4, and therefore we see it's invertible because we know that a matrix is invertible if and only if the determinant is non-zero. So it's invertible because the determinant of A is not 0. And the last question is A orthogonal? So what does orthogonal mean? Orthogonal means that the columns of this matrix A are orthogonal to each other, but this is not the case because we see, for example, that this first column, if I take the dot product with the second column, this is just 5, which is not 0. So the answer here is no. Okay, maybe I would not write this down. You can also find the solutions online, and there it's a little bit more detailed. And here I just want to sketch the ideas. Okay, so this was exercise 1, and now exercise 2. So exercise 2 is some kind of multiple choice, so you should decide if the statement is true or false, and then give a small explanation why this is true or false. And so let's start. So these are 11 true or false questions, and let's now start with number 1. And this question here is, if this set here, consisting of all polynomial functions of degree 2, such that the value of this function at 1 equals the value of this function at 2, is this a subspace of all polynomial functions of degree smaller or equal 2? And this is true, because to check if something is a subspace, we need to check two things. Namely, if I take two elements out of the set and I add them with this vector addition, is this again in this set? And we need to check that if I take an element out of there and multiply with a scalar, that this is also again in the set. But here, for example, if f and g are in U, this means f of 1 equals f of 2 and g of 1 equals g of 2. Then what is, let's say, we say h is f plus g. Well, h of 1 is then f of 1 plus g of 1. Oops. But then, because f is in there, this is f of 2, and because g is in there, this is g2, and this is by definition h of 2. So h also satisfies this condition that h of 1 equals h of 2. And also you see that if you multiply some element f with some lambda, then of course lambda f of 1 is the same as lambda f of 2. Okay, so the first statement is true. So maybe just put this here, true. And now the second statement, the set of matrices, of 2 by 2 matrices, which have eigenvalue 1, question, is this also a subspace? And here the answer is no. So this is false, because you, in this case, the identity matrix is in U. But if I multiply it with 2, for example, 2 times this identity matrix, this is not in U, because the eigenvalues of this matrix are 2. So this statement is false. And third statement, every 3 by 3 matrix has 1 eigenvalue, and this is true, because the characteristic polynomial of a 3 by 3 matrix is a polynomial of degree 3, and every polynomial of degree 3 has at least one real 0. And therefore we have a real eigenvalue. So this I will not write down. Statement number 4. For any subspace U, there exists a linear map F such that this subspace U is given by the kernel of this linear map. And this is also true. I think this was also part of some homework, but if I have some subspace U, then I can write down a basis of U. So let's say U1, UL, basis of U. And then we learned that if we have a basis of a subspace, then we can extend this to a basis to the whole space. So we can add some vectors, v1 up to vm, such that this is a basis of the whole space, V. And now I can define a linear map F from V to V. So if I define a linear map, I just need to say what it does on the basis. And what I will do, I will send the UJs to 0, and the VJs I just send to itself. And then you will see that the kernel of this map is exactly the span of the U1 up to UL, and this is exactly the subspace U. So here the kernel of this F equals this U. So this works in general. So every subspace is the kernel of some linear map F. Okay, so this was 4. Number 5. So there exists a linear map F such that the dimension, so F from R3 to R3, such that the dimension of the kernel of F equals the dimension of the image of F equals 2. And this is false because we learned that the dimension, in this case of the whole space, R3, so this is 3, equals, if I have a linear map from one vector space to another, then the dimension of the space equals the dimension of the kernel plus the dimension of the image. And therefore both of them cannot be 2, because otherwise 2 plus 2, this doesn't work out, because it has to be 3. So we learned that if the kernel gets bigger, then the image gets smaller, and vice versa. So and the sum of both of them is always a fixed number. In this case, it's 3. And number 6. So let's assume we have two bases of a vector space V. So this is a two-dimensional vector space, because the number of elements here in the bases are 2. Then the question is, if I take the sum of the first entries here and the difference of the second entries, is this also a basis of V? And this is false, because we could say that C1, or that C2, and that C1 equals B1 and C2 equals B2. And in this case, this vector here, B2 minus C2, would be 0. And 0 is never a part of a basis, because 0 is linearly dependent with any other vector. So this is clearly false. And next question, if the determinant of a matrix is 0, then A has at least one eigenvalue. And this is true, because in this case, when A has determinant 0, then 0 is an eigenvalue of A, because the characteristic polynomial of a matrix A at 0 is by definition exactly the determinant of the matrix A. And if the determinant is 0, then the number 0 is a 0 of the characteristic polynomial. So in other words, 0 is an eigenvalue. So if this is 0, then 0 is eigenvalue. Okay, number 8. If the determinant is 0 if the determinant of a matrix A is 0 and the determinant of a matrix B is 0, then the determinant of A plus B is 0. And this is again false, because, well, we could take A to be 1, 0, 0, 0. This has determinant 0, and B could be 0, 0, 0, 1. This has also determinant 0, but A plus B is the identity matrix which has determinant 1. And number 9, there exist symmetric matrices without eigenvalues, and this is false, because this is exactly the spectral theorem we had, where we had the statement that any symmetric matrix is diagonalizable. So in particular we can find a basis out of eigenvectors, and this in particular means that we also have eigenvalues. And yeah, every orthogonal matrix is invertible, and this is true again, because we know that if a matrix is orthogonal, then we can write down the inverse quite explicitly. Namely, if A is orthogonal, then the inverse is just given by the transpose of A, and this was due to the fact that the columns are orthogonal to each other. So if I place columns and rows and multiply this matrix, then I get exactly the identity matrix. And the last one, if I have a linear map F, and I compose this, so I apply this map twice, and if this has at least one eigenvalue, then F also has at least one eigenvalue. And this is false. For example, so this is false, because if I take this map here from R2 to R2, F, which sends a vector x to, let's say, this matrix, so here this matrix A, the determinant, the characteristic polynomial of this, so P F lambda is lambda squared plus 1, so this doesn't have any zeros. But if I apply F twice, so what does F circle F do? So you see that this just sends x to -1, -1, 0, 0, x. So this here, this has an eigenvalue, namely -1. So in this case here, this applying F twice, this F circle F has an eigenvalue, but this F doesn't have an eigenvalue. And here we can see that in this case, the eigenvalues of this here, if you allow complex numbers, are I and -I. And if I square I and -I, then I get exactly these -1s. Okay, so this is exercise 2 with true and false. And now exercise 3, where we do some examples, or where you should give some examples of certain things. So first, give an example of a linear map from R2 to R2, where the dimension of the kernel of F equals the dimension of the image of F equals 1. So first we notice that this actually exists, because we just discussed that the sum of the dimension of the image and kernel need to be the dimension of the whole space. So in this case 1 plus 1 equals 2. So this exists, and we see that, for example, we could choose the simple map which just sends the vector x1, x2, for example, to x1, 0. Then we see the kernel is the span of this vector here, and the image is the span of this vector here, and both of them are one-dimensional. 2. A matrix which is not symmetric but diagonalizable. So, for example, we can choose this here, and this will be part of exercise number 4. So there we will diagonalize this matrix, but this matrix is clearly not symmetric. And then a linear map from P1 to P1, so the polynomial functions of degree smaller or equal to 1 without eigenvalues. And so there we can choose the following. So if you want to give an example of something without an eigenvalue, then you should always have this matrix here in mind, because this was our standard example of a matrix without eigenvalue, because the characteristic polynomial is lambda squared plus 1. So now we need to find a linear map from P1 to P1, which such that the matrix of this linear map has exactly this shape here. And but I need to say what I do to a polynomial function of degree 1. So I need to say what I do, for example, with at plus b, or let's say x. So in this here I can send to, for example, minus bx plus a. And then you can see if we choose the basis b to be 1 and x, so this is the basis of the space P1, then this matrix here is exactly this f, the matrix of this f with respect to the basis b. And therefore we see that we don't have any eigenvalue. And last one, number 4, an orthogonal matrix, a 2x2 orthogonal matrix without 0 as an entry. Well, we can choose, for example, this one. So first we see that this vector is orthogonal to this vector, but we also want that the norm of both of these columns is 1. And so what is the norm of this? This would be the square root of 2, and also this would be the square root of 2. So in this case, if we divide out the square root of 2, then this would be an orthogonal matrix without any 0 as entry. Okay. Exercise number 4. So in this exercise, we want to solve a discrete linear system. So we define the vector xn for all n greater or equal to 0 as follows. We say x0 as this vector 1, 0. And then xn plus 1 is always m times xn, where m is this 2x2 matrix here. And the goal is to determine an explicit formula for xn. So this is similar to the Fibonacci example, where we also had these Fibonacci numbers where were defined recursively like this. And we also had a matrix, a 2x2 matrix, which looked something like this. Yeah. And the idea to solve this was to diagonalize this matrix M. So first notice that this xn is given by the m's power of m times x0. And so what we want to diagonalize m. So we want to find a matrix S such that S inverse times M times S equals some diagonal matrix D, because then this m to the power n will be given by S d to the power n S inverse. And we know how to do this. So this matrix S will be just given by, the columns will be given by eigenvectors, and the entries of this D, which will be the diagonal matrix, will be given by the corresponding eigenvalues. So therefore we need first calculate the eigenvalues of this matrix M. Then for each eigenvalue the eigenvector. Then we can write these eigenvectors in the matrix S. And then we already know that this works. But in the end then we want to calculate this explicitly to give this explicit formula for xn. So let's do this. So eigenvalues. So we need to consider the characteristic polynomial of m, which is the determinant of 1 minus lambda, 3, 1, 1, 3, 3 minus lambda. So this is 1 minus lambda times 3 minus lambda minus, oops, what's that? Minus 3, and this is lambda squared minus 4 lambda plus 3 minus 3 minus 3. So the 3 cancels out, and we have this is lambda times lambda minus 4. So the eigenvalues of this matrix are 0 and 4. So lambda 1, let's say, is 0, and lambda 2 is 4. So now the eigenspaces so for the 0, this is just the kernel of M. And this is just the kernel of 1, 1, 0, 0. And this is a span. Well, what is the kernel of this? So, in other words, what vectors can I multiply here with this matrix such that I get 0? And clearly I need to have that the first entry is the negative of the second entry. So this is exactly the span of the vector 1, minus 1. And the eigenspace for the eigenvalue 4 of this matrix M is the kernel of M minus 4 times the identity matrix. So this is the kernel where I subtract here 4. So 1 minus 4 is minus 3, 1, 3, and 3 minus 4 is minus 1. And again, so I need to consider the row-reduced echelon form of this matrix. So I can add this to there, so I get a 0 row there, and then I can divide by minus 3. So this is the kernel of 1 minus 1/3, 0, 0. And this is the span of all vectors where the second entry is 3 times the first entry. So this is 1, 3. So now I have 2 eigenvectors. And we learned that eigenvectors, well, it's clear that these 2 eigenvectors in this case are linearly independent. So if I write them in a matrix, so here 1 minus 1, 1, 3, then this matrix is invertible. And we also learned that in this case S inverse times M times S equals the matrix where I have exactly the eigenvalues on the diagonal. So here, because I put the eigenvector of the eigenvalue 0 in the first column, I get 0 here in the first entry. And because I put the eigenvector for the eigenvalue 4 in the second, I get the 4 here. And this is our matrix D. So we have that M to the n equals S. And now I need to take D to the nth power. So here this is for n greater or equal to 1. So this is 0, 0, 0, 4 to the n, S inverse. And now we want to multiply this with x0, because our goal is to calculate xn, which is given by m to the nth power times this start vector 1, 0. So let's calculate S inverse, because we need to calculate this because we want to multiply this with 1, 0 here. And how do we calculate the inverse of a matrix? Well, calculate S inverse. So the idea was to write S on the left hand side and here the identity matrix I2. So here we have 1, 1, minus 1, 3, and 1, 0, 0, 1. And then we need to bring this on row-reduced echelon form. So here we add the first row 1 time to the second row. Then we have 1, 1, 1, 0, 0, 4, 1, 1. And now we can divide here by 4. So we have 1, 1, 0, 1, 1, 0, 1 over 4, 1 over 4. And now we can subtract the second row from the first, and we get that here on the left hand side we now have the identity matrix, and on the right hand side 1 minus 1 over 4 is 3 over 4, and minus 1 over 4, 1 over 4, 1 over 4. So in other words, S inverse is given by 1 over 4, 3 minus 1, 1, 1. Okay, so now we have every ingredient for this thing here, and we can multiply this with x0. So m to the n times x0 equals s 0, 0, 0, 4 to the n. And now S inverse, maybe I can write it directly. So S is what? S is 1, 1 minus 1, 3. So this is S. And S inverse is the thing we just calculated. And the 1 over 4 we can put in front. So we have this is S inverse. And we want to multiply it with x0. Okay, so we have this. So now let's multiply this out. So this, multiplying this matrix with the vector 1, 0 just means we take the first column of the matrix, and then we multiply this out, the matrix here with this vector there. So this 3 just gets multiplied with 0, so we just take this here. So this is 0, 4 to the n. And then in the end, we see that if we multiply this vector with this matrix here, so the first column doesn't play any role, and we just multiply 1, 3 with this 4 to the n, so we get 1 over 4 times 4 to the n, and here it's 3 times 4 to the n. So we can put this 4 to the n in front and get 4 to the n minus 1, 1, 3. And this is our end result, because this is now xn. Okay, so that's this. Okay, so let's do exercise number 5. And this is given a linear map from P2 to P2 as follows, where we send a polynomial function p to evaluated at t to t times the first derivative of p plus 2 times p. And we want to calculate the determinant of this f. And what is the determinant of a linear map? Well, for this we learned that we can choose any basis, and then the determinant of this linear map is the determinant of the matrix of this linear map with respect to this basis. And in this case we choose our standard basis, the basis 1 x squared. So this is b1, this is b2, and this is b3. And we want to calculate f, the matrix of f, with respect to this basis here. So we need to see what is f of b1, for example, of t. Well, b1 is just 1, so the derivative of this is 0. So it's 2 times the just 1. So this is 2, which is 2 times b1. So here the first entry is 2, 0, 0. Because here it's 0 b2 plus 0 b3. Well, what is f of b2? T? Well, this is t times the derivative of... Oh, I should maybe call these also t. Sorry, t and t squared. So what is f of b2? It's t times the derivative of b2, which is 1, so it's t plus 2 times t, which is 3 times t. And this is 0 times b1 plus 3 times b2 plus 0 times b3. So if 0, 3, 0. And also similar, you can check that what is f of b3, where you take t times the derivative of this. The derivative of this is 2 times t, So let's write this down. B3. So it's where t times 2t plus 2 times t squared. So this is this is 4 times t squared. So this is for b3. So we have 0, 0, 4. And therefore the determinant of f is by definition the determinant of f, of the matrix of f with respect to some basis, and in this case it's 2 times 3 times 4, so it's 24. Okay. Now exercise number 6. Let V be a finally generated vector space, which actually doesn't play a role here, and consider a linear map P from V to V, which satisfies the property that if I apply P twice, it's the same as just applying P. And now we assume that lambda is an eigenvalue of P, and we ask what are the possible values of lambda. So if lambda is an eigenvalue, this means there exists a V in V, such that V is not 0, with the property that P of V equals lambda V. So what now what is P of V? So we can evaluate this now in 2 ways. So one way would be to use this property here. Well, so here this is P circle P evaluated to V. So the definition is to just apply P twice. And using this property here is that this is the same as P of V. So in other words, this is lambda V. But now we can also evaluate it as follows. So we know P of V equals lambda V. So this is P of lambda V. And P is a linear map, so we can put this lambda in front, and this is P of V. And now we can use it again, that P of V equals lambda V. So therefore this is lambda squared of V. So therefore these two are the same. So in other words, lambda squared times V equals lambda times V. So in other words, lambda squared minus lambda times V equals 0. But because the V is an eigenvector, meaning this is particularly not the 0 vector, and if we have some number times a non-zero vector, which gives us a 0 vector, then this means that this factor here needs to be 0. So here we use that V is not 0, and therefore lambda squared minus lambda equals 0. Or we can also write this as lambda times lambda minus 1. But then we see the only possible choices for lambda is that lambda is 0 or lambda is 1. So the answer to the question, if lambda is an eigenvalue of P, such that this property is satisfied, then the only possible choices for this eigenvalue is either lambda is 0 or lambda is 1. Good. Now, final question. Find all solutions to the following differential equation, such that the value of f at 0 and the value of the first derivative at 0 and the value at the second derivative at 0 is 0. So, but first we ignore these conditions here, and we just want to find all solutions to this linear differential equation. And the differential operator here, in this case, is d cube minus 2d squared. So recall d is just the map which sends f to its first derivative. And we want to solve the differential equation tf equals 4. And the strategy to solve this kind of linear equation was to find one particular solution, and then all solutions are given by this particular solution plus all elements in the kernel of T. So let's start with the particular solution. So we want to find one solution of this equation here. And here on the right hand side we have a number. So one naive guess would be, well, we can try a polynomial, because if I take the derivative of polynomials and add them, I will get a polynomial, and 4 is a polynomial. And in particular, here one choice would be to take a polynomial of degree 2, because the third derivative of a polynomial of degree 2 is just 0, and the second derivative of a polynomial of degree 2 is just the number, and therefore we can choose this number in such a way that minus 2 times this number is 4. So we make the ansatz that the particular solution fp of t is some a t squared plus bt plus c, but we can already ignore these terms here because in the second derivative and the third derivative they will vanish. So we can actually just make the ansatz that fp of t equals a times t squared. So what is the third derivative of this? Well, this is 0. And the second derivative of this, well, it's just 2 times a. And therefore, if we want this equation here to be satisfied by this fp, we want that minus 2 times 2a, so minus 4 times a equals 4. So for a equals minus 1, we get that t of fp equals 4. So in other words, we choose fp to be minus t squared. So this is one particular solution. And now all solutions are given by this one solution plus all elements in the kernel of t. So therefore we now want to do the kernel of t. And how do we do this? Well, for this we consider the characteristic polynomial of this differential operator, which we denoted by pt of x, and in this case is x cubed minus 2 times x squared, and this we can factor as x squared times x minus 2. And now we use the result from the lecture, which I have here, stating that if the characteristic polynomial is given by this here, so I have some factors to the power m, some lambdas, lambda 1 up to lambda r, which are different. So in this case here, I have lambda 1 is 0, and m1 is 2. So here I have x minus 0 to the power 2, and I have lambda 2 equals 2, and m2 equals 1. So here I have the 1. And then the statement was that for this here, I get 2 elements in the kernel given by, so here this theorem gives the kernel of t equals the span. So here from lambda equals 0 and m equals 2, I get e to the 0t and t times e to the 0t. So this is just 1, and this is also just 1. Well, vertical 1. And here, from this lambda 2 and m1, I get one function, namely e to the 2t. Oh, it's a different color. I get e to the 2t. And these 3 elements are actually a basis of our kernel. So let me write this again. So this is 1, t, and e to the 2t. And depending on the exponent here, we get always, if the exponent is m, then we get m functions, where we have e to the lambda t, and then times 1, e to the lambda t times t, up to e to the lambda t times t to the m minus 1. But in this case, m is 2 and the other m is 1. So therefore, all solutions of this differential equation tf equals 4 are given by f of t equals our particular solution, so this is fp, plus, and now all elements in the kernel, meaning some linear combination of this 1 plus some multiple of this t plus some multiple of this e to the 2t, where c1, c2, c3 are real numbers. Okay, but now let's go back to the, we want this condition here. So want to find C1, C2, C3 such that this. So let's first consider what is the first derivative, where the first derivative here, so this is minus 2t, this c1 vanishes, so this is just c2 here, and here we get a factor 2, so this is 2 times c3 e to the 2t, and the second derivative is minus 2 plus, where this c2 vanishes, and here for c3 we get another 2, so we get 4 c3 e to the 2t. So f of 0 equals, well, we need to plug in 0 here. So 0 here is meaning this is 0, this is 0, and this is 1. So we just have c1 plus c3. F prime of 0, this is 0, this is 1. So we just have c2 plus 2c3. And f2 prime of 0 is minus 2 plus 4c3. And we want that all of these are 0. And this is just solving a linear equation now. But we can see here, this is quite easy to solve, because here in this equation we just have c3. So from this equation we already see that c3 needs to be a minus 1/2, sorry. And then if c3 is 1/2, then c3 times 2 is 1, so c2 needs to be minus 1. And if c3 is 1/2, then c1 needs to be minus 1/2. So the final solution is, if we take this one here, bring it here, our c1 is minus 1/2, so minus 1/2. Our c2 is minus 1, so we get a minus t here, and c3 is 1/2. So we get a 1/2 here. And therefore this function here satisfies the equation that that the third derivative minus 2 times the second derivative is 4, and also that it's 0 at 0, so if we plug in 0 here, we get minus 1 plus 1/2 is 0, and the first derivative at 0 is also 0, and the second derivative at 0 is also 0. Yeah, and that's all for the review exercises, and also everything for this course. So yeah, we will see in the final exam. See you then.